So here's the outline of this video about this lock-in amplifier measurement of ESR of the capacitors. So we'll talk about initially non-ideal effects in capacitors such as ESR, series inductance, and see how that compares with a simple simulation setup. Next, I'll go into setting up the lock-in amplifier for the ESR measurements. Then we'll do some actual lock-in amplifier measurements and then compare them with a handheld LCR meter. And finally, I'll attempt to measure the ESR of a supercapacitor. This is going to be a fairly long video, so if you're very familiar with these topics, please skip ahead to the actual measurements if you're interested. Otherwise, stick around and go through this long presentation. So before we go into the actual measurements of the capacitor on a lock-in amplifier, let's review a few equations relating to the ESR, to the capacitance, as well as the phase angles of the voltage and currents, because that will become important in the actual measurements of the ESR and other parameters like the Q and dissipation factor and so on. So here we have a three-element capacitor designated with the two parasitic components, the inductor and the resistor. The resistor is RC, which is also the equivalent series resistance. C is the actual capacitance. We assume that this is a dominant factor in the whole device, that is basically a capacitor and not a resistor or inductor. So the impedance of this will dominate the overall current profile. So if we apply a voltage A sine omega t, we will have a Vc, that is the voltage across the capacitor, and then there will be some voltages across these two as well. Now the impedance, if we ignore the LC for the moment, because that's a much smaller component and doesn't play a huge role at low frequencies, we can then say that ZC, or the impedance, is equal to RC plus minus J over omega C, where omega is equal to 2 pi f, where f is the frequency of the sinusoidal signal. ZC then can be rewritten as omega RCC minus J over omega C, and if you want to compute the current, then you have the Vin divided by ZC, then that becomes Vin times omega C over omega RCC minus J, and that, if you simplify, you get into the final equation over here, which is omega C squared omega squared C squared RC over the denominator, which is 1 plus omega squared RC squared C squared, plus the J term, which is the imaginary axis term, or the reactance part of it, which you get omega C over the same denominator times Vn. Now we can simplify further. If you want to just look at an ideal capacitor, you basically make RC equal to 0, in which case you get Vn times 0. The first term goes to 0, the real part. The only thing left is the J omega C. From this omega C over 1, this goes to 0, and so we have a current of IC, which is Vn J omega C. This implies, the J implies it's positive J, that means the current is leading the voltage by 90 degrees. So we just derived the impedance of a capacitor in terms of the resistance, ESR, and capacitance, and the frequency and so on. So but let's quickly look at one more thing, and that is the phasor diagram of the impedance itself and how it's affected by the reactance and the resistance. So the real axis, we have the resistance here, the x-axis, and the imaginary axis, the j-axis, we have the reactance. So in the original case where there's no inductor, the black lines will indicate the vectors involved. So we have xc, which is the capacitive reactance, which is negative, and you have R ESR, which is RC, which is the positive resistance here. So the sum of these two vectorially will result in this ZC or ZC, which makes a phase angle of theta 1 degrees with respect to the real axis, negative, indicating it's a capacitor. Okay. Now when you add the inductor has a positive reactance, so that's XL, and I'm assuming it's quite a bit smaller than XC, so it's this capacitor is still acting like a real capacitor, and the inductor is just a parasitic element. So now because these two are exactly 180 degrees apart, you can basically subtract or add them numerically, one being positive, one being negative, so you get a slightly smaller reactance which is still negative but turns out to be XL minus XC. So since R isn't changed, now we have a new vector which is going to be slightly smaller. The theta 2 is going to be smaller than theta 1. That results in a higher loss, which is indicated by the delta, which is 90 minus theta. In this case 90 minus theta 2, which is a larger angle. So effectively, by adding a inductor, you're making the capacitor worse. That is, you're decreasing the reactance. So you're actually increasing the loss, the resistance becomes the larger portion of the reactance. So purely from a measurement point of view, I've done some measurements on capacitors with inductance added to them in series, and that basically has resulted in a measurement that is indicating a higher capacitance. So I'm thinking this is a measurement effect, possibly not a real effect, because what is going on is that when a measurement is taken by an instrument, it's trying to read the capacitance of that particular device, and is somehow measuring the energy in that particular thing. Effectively, it comes down to measuring the energy and then converting that to some into a capacitance value. So if you look at this non-ideal capacitor, we have a UC, which is the energy in the capacitor, has half CV squared, and energy in the inductor is half Li squared. They are both positive numbers, so they will add and they will not cancel out any portion of each other. So if you look at the energy in the total energy, you get UC plus UL, which is happening when you have a sinusoidal input driving this capacitor. You have the inductor and the capacitor basically out of phase on each other in terms of current and voltage, but the total energy is still going to be half of CVC squared plus Li squared, and that energy is going to be constant as far as the total energy is concerned. Now if you want to then if the measurement is being done by an instrument, it has to report a capacitance value, and so that capacitance you can basically assume is got the total energy of the capacitor and the inductor in it, and that if you then equate the capacitance, the new capacitance value equal to the sum of these two energies, you can then derive Cx, which is the equivalent capacitance, as CVC squared, which is the voltage across the capacitor, plus Li squared, which is the inductance times the current squared, divided by Vc squared. So that Cx is now going to be larger than the original C, because you have this Li squared term added to it, which implies that Cx, if it's larger than C, then you're going to have the reactance, the capacitive reactance, to be less than the original reactance of X of the C itself. So what happens is that you have a decrease in the Q and increase in the dissipation factor, because this capacitance is now has increased, and that is actually even reported by the meter. So it's again not clear to me whether this effect is because of the fact that this energy is being attributed to the capacitance itself. So what I'm showing on the right over here is the original capacitor here, which has the capacitor, resistor, and the inductor, and once you do this conversion, you get a new capacitor which is larger than this C, but it's the inductor is gone, the energy is absorbed into this value, and then RC remains the same. So for the purpose of demonstrating this effect of inductance, which changes the capacitance of a capacitor, I'm going to have two components. One is a real inductor, which is going to have some sizable inductance, and then a capacitor, which is going to be fairly large. So this combination of these two will still be a very strong capacitor, but this will add significant inductance, which can make a difference in the measurement. So effectively, we have in the inductor we have a series resistance, which is small, but probably less than the in series resistance of the inductor, capacitor RC, and we have a, I'm going to neglect the inductance in the capacitor, which is going to be very, very small because the leads are very sharp. And the only things to consider are then the inductance, which is the L inductance, the main capacitance C0, and the sum of the resistance of these two components. So our ESR effectively becomes RC plus RL, and from the previous formulas I'm going to convert the C0 into Cx by incorporating part of the inductance, the energy in the inductance, into the capacitor. And if the measurement shows that it's actually increasing in the value of Cx, it proves that the inductor actually degrades the performance of the capacitor, both in terms of not in both, but in terms of mostly the dissipation and the quality factor, but effectively changes the capacitance that is measured, although I'm not quite sure if that is what is the real effect in the system. So here I have a 470 microfarad electrolytic capacitor. It's got very short leads, so the inductance on this one is going to be, the effect of inductance is very, very minor. So in order to simulate the effect of inductance, I'm going to add this inductor in series when I do the measurement to see the effect of what we talked about in terms of the worsening X total reactance, decrease in reactance, and then the effect of increase in capacitance because of this inductor, and also making it lossier in terms of the value of the dissipation factor and reduction of the quality factor. So before we do that, go to the lock-in, let's do the measurement using this LCR, handheld LCR meter. This is quite accurate for certain frequency ranges, and once we do this and confirm that the effect of this inductance will actually increase the capacitance seen by the meter, will prove the previous discussion we had on the effect of this inductance. So let's measure the capacitance first. So we have a capacitance of 440 microfarad at 1 kilohertz. So we'll do the measurement at 1 kilohertz. So we have 440 microfarad and dissipation factor of 0.281. The Q is the inverse of this, that is 3.54. ESR 0.1 ohm, and the theta angle, that is ideally it will be 90 degrees if it were lossless, but this is minus 74.2 degrees. So this is for the cap. So ideally 470, probably this value will be true at a lower frequency. Now we'll do the measurement of the inductor. So the inductance at the same frequency, 1 kilohertz, is 14.3 microhenry. The Q is 4.45. ESR is 0.02 ohms. Theta, now this is a positive number which we expect, 77.3 degrees, and the D is 0.223. Okay, so now I've connected the two in series. So this inductor acts like a very long lead as far as this capacitor is concerned. So I'm just trying to enhance the effect of inductance to prove my point. So you can see now that the value of the capacitance read is 585 microfarad. So Cx, or the C effective now, is 585, and the dissipation factor, as I said, increased to 0.0455. The Q is now fallen to 2.19, and the ESR is 0.12, which which if you recall from previously we had 0.1 ohms and 0.02, so that makes sense. And the phase angle has decreased from the minus 74 to minus 65.4. So effectively these meters are actually measuring the energy in this system and calculating the effective capacitance for this combination of RLC network. This slide shows the simulation schematic for the previous experiment I just ran using the capacitor and the series inductor. So the capacitor is C1 over here, which is 440 microfarad. It was measured as 440 microfarad on the DE5000. The series resistance is equal to the two combination of the inductor and the capacitor, and the inductor is 14.3 microhenry. The frequency is 1 kilohertz. The series resistance of the source, or the source resistance, is 50 ohms. The amplitude of the sine wave is not important, but the frequency is 1000 hertz, 1 kilohertz. So when I simulate this, essentially I'm simulating the series combination of both these components, the inductor and the capacitor. I also did individual simulations of just the inductor and the capacitor, and I will show the results of all three of these simulations in the next slide. So essentially what I'm trying to do here is to correlate or make sure that the measurements that I'm doing is also corroborated by simulation, and the same equations are being used either by the instrument, the DE5000, and I'm able to recalculate back all the values correctly, such as ESR and phase angle or whatever else I want to do. This slide is now the summary of the results I got from the DE5000 and the simulation. The first set of data is for the capacitor itself, the 470 microfarad capacitor, measured as 440 on the DE5000, and I plugged in this value into the simulator. The Q was measured as 3.54, ESR is 0.1 ohms, and theta angle, which is the 90 minus theta gives you delta. The theta angle came out to be minus 74.2 degrees. If you compare with the simulated values, I was actually getting very close to those values, which confirms that my simulation is working correctly, and I can use this to basically do the next calculation, which is the combined series inductance and capacitor. The toroidal inductor measurement simulation came out to be also very close, 14.3 microhenry. The Q was 4.06. ESR came out to be 0.022, and the theta was 76.2 degrees compared to the values on the left, which show the DE5000 measurements. And finally, the series combination of the above, you can see that the CX, the effective capacitance I talked about, was measured as 585 microfarad. Q was 2.19, ESR 0.12, and theta angle 65.4 degrees, which showed the worsening effect of adding the inductance. Now the simulation then came out as 549 microfarad, a little bit off, but still not too bad. The Q was fairly good, 2.25, ESR 0.16, and the phase angle was very close, also minus 66 degrees. So to summarize, the effect of inductance can be pretty severe, especially as you go into higher frequencies, since inductive reactance starts to increase and capacitive reactance starts to decrease, and then they tend to cancel out, and then you get these weird results in terms of the capacitance, actual capacitance result, because the energy of these two components are about the same, and so you get almost like a doubling of the effect of that in terms of energy, and so the capacitance will increase. The ESR does not change much. It will basically still continue to be the lossy component in this network, but then your capacitance measurements don't make sense anymore at higher frequencies. So before I go and measure these capacitors on a lock-in, I'm going to measure another capacitor. This is a very large one. This is rated this is a 6.8 millifarad or 6800 microfarad cap, 6.3 volt, and we're going to measure this on this handheld meter first, see what we get, and then we will go ahead and do it on the lock-in and compare the results. Of course, this can only measure at certain frequencies, so let's see what we get for the different frequencies. So starting with 100 Hertz, where this capacitor is most likely to be used for mains filtering on linear supplies typically. So we have at 100 Hertz we have 6.67 millifarad, a D of 0.247, Q of 4.04, ESR of 0 ohms. Doesn't have the resolution, I guess, to display anything less than 0.01 or so, 0.1. And theta is equal to minus 76.1. So from this number, it could probably go back and calculate the actual ESR, which is going to be, I guess, like 0.05, 50 milliohms or so. The next frequency is 1 kilohertz. I'm not getting a reading here. Let's see if anything else comes up. 10 kilohertz, nothing. 100 kilohertz, nothing. So basically, at these higher frequencies, the reactance becomes too small, I guess, for it to be able to measure it accurately enough to even display any capacitance values. It might think it's an inductor actually, so if I make this as an inductor, it might show some readings. Let's try that. There you go. So actually it reads this as an inductor, probably because the reactance is so large, it's become more positive reactance, so I'm guessing it's acting like more like an inductor at this frequency. Anyway, I'm not going to note that for now. I just want to see what happens. Yeah, so it does go back to being a capacitor at 100 Hertz. So anyway, so that's the experiment I wanted to do before I went to the lock-in with this large cap. So here's my setup for the lock-in measurement. I have the source at the bottom, the HP3325A synthesizer, putting out 100 Hertz, and the amplitude is right now 100 millivolts RMS, and it will show up as 200 millivolts because it's unterminated at this point. So this is a clock going into the reference input of the lock-in, and this is the signal that I'm going to be applying to the capacitor, but right now it's connected directly to the A input of the lock-in. And basically I want to, before I start the measurement, I want to zero out the phase, so make sure that the reference signal and the reference clock and the signal are in phase before I start the measurement. So to do that, I'm going to align. This is right now showing a 10.9 degrees of phase difference, so I need to make that 0. So I can do that by reducing this phase by 10 degrees. Okay, so now you can see that the phase is close to 0.1. Amplitude is 199.3 millivolts, and those two numbers look good. So now I can connect the capacitor and see what we get. So I'm going to be connecting the capacitor just across this terminal coming out of here, across these two, and the voltage will of course drop because the capacitance will effectively short this source. The source impedance is 50 ohms, so this will drop to microvolts, millivolts, whatever. We'll see what happens. Okay, almost there. So it's now connected, the capacitor is connected, and of course I'll reduce the scale here. So this is the 1 millivolt scale right now. So on the 1 millivolt scale I'm reading 0.93 millivolts, and a phase angle of minus 75.8 degrees. So this is 100 Hertz. I'm going to write this down over here. The amplitude is 0.931 millivolts and the phase angle theta is minus 75.9 degrees. Now I can repeat this at the higher frequency, and I'll come back, and once I've recalibrated the phase for this lock-in at the higher frequency. So right now the synthesizer is putting out 1 kilohertz, and I can see that the reference is measured at 998, and the amplitude is now 191 millivolts. The phase is 0. So now we'll connect the capacitor again. So this time we expect the voltage to drop even further because the capacitive reactance would have dropped at 1 kilohertz. Now look at the signal. The received signal is dropped to 205 microvolts, and as you can see the phase angle is really bad now. It's minus 28.4 degrees, so it's getting to be quite resistive at this point. So this is 1 kilohertz. Let me write this down. The signal is 206.1 microvolts. Phase angle is minus 28.5 degrees. So this is now 5 kilohertz. I'm going to connect the cap again. Okay, the cap is connected. Voltage has dropped. It's even dropped further down to 160, 172.3. Okay, 173 microvolts. Phase angle is now almost 0 degrees, getting down to like 6.5 degrees, minus 6.5. So it's acting almost like a resistor right now. So 173.7 microvolts and minus 6.5, 6.4 degrees on the phase. And here's now the final results from the lock-in measurements compared with the DE5000 LCR meter. At 100 Hertz, for example, the DE5000 was 6.67 millifarad compared to the 6.77 millifarad for the lock-in. The Q was very close, 4.04, 4.105. ESR on the DE5000 was reported as 0. It didn't have the resolution probably to display it, whereas the lock-in, I could calculate that to be 0.057 ohms. Theta was very close, so it agrees very well with the D5000 as well. And finally, I also calculated the capacitive reactance, which then came out to be 0.228 ohms, which is basically still indicating that this is acting like a capacitor, where the ESR is smaller than the capacitive reactance. At a higher frequency, at 1 kilohertz, the DE5000 could not measure anything, whereas the lock-in was able to get a value of almost 3 millifarad out of that capacitor. The Q is now dropped to like 1.14. It's almost useless as a capacitor now. ESR is 0.047, decreased a little bit, but I don't trust this too much at this point. Theta is now down to minus 28.5, which makes it appearing more like a resistor now. XC is now dropped even further to 0.026 ohms, and this is basically indicating that now you don't have a capacitor anymore, or the capacitor is not effective because the ESR is much larger than the reactance of the capacitor. Finally, at 5 kilohertz, the capacitance was down to 704 microfarad, 1/10 of what it should be. Q is now 1. ESR is about the same. Theta is minus 6.5 degrees as we measured earlier, and XC is now 5 milliohms, so it's basically a dead short at this frequency as far as capacitive reactance is concerned. So with all of this, it's clear that lock-in can do measurements pretty easily. The only thing is you have to do the calculations yourself, but it gives you the flexibility of doing it at any frequency you want. Potentially you can add DC bias to the cap and do some measurements that way, and to get an idea about how it performs under DC biasing conditions where the ESR is likely to change negatively, that is, as far as performance is concerned. So my last experiment is going to be to try and measure the ESR and capacitance of a supercapacitor. I don't expect it to work because I cannot go low enough in frequency to actually do this. I did some calculations to figure out how much I would need to go down to reasonably measure the capacitance, and I would need to go to like 10 millihertz, which is well beyond the range of this particular lock-in amplifier. And the capacitor is really this bunch of 500 farads in series, and a 12 volt capacitor, supercapacitor, and which has a effective capacitance of around 83 farads. So I've covered it in tape so that I don't accidentally drop some metal on it and short it up. This is 2 hertz on the lock-in amplifier. The phase is close to 0 with the reference going back, or the signal going into the without any attenuation directly back into the lock-in signal input. Now I'm going to connect the capacitor and see what happens. So the capacitor is connected. Now I'm going to connect the source. Be a dead short for the source, so make sure your source can handle this. This is a 10-second integration time, so this is going to slowly drop off. Now if I decrease the signal amplitude, let's see what I get. So it's seeing some signal there, but I can't trust it at this point. So the phase has not changed very much, it's still around 0. But I'm getting a signal on the voltage side of it. It's about 1.3 millivolts. So it's about a minute later now, and amplitude is settled at around 1.43 or 1.42 millivolts. The phase is still around 0. So I don't expect any good results out of this. So to summarize the supercap results, basically because of the extremely high capacitance, we got very low capacitive reactance even at power line frequencies like 50 Hertz, 60 Hertz. So I think these caps are good for energy storage, not meant for any AC filtering. It's impractical to really measure the ESR using an audio frequency lock-in amplifier. They're good for energy storage applications where you're drawing a large amount of current. So if you want to measure the effective resistance of these caps, you could probably just load them using a large current and then measure the voltage drop, internal voltage drop that is seen at the load, and so that would be a practical way of actually evaluating supercaps, I feel. Just to make sure that my setup is working, I connected this 6.8 millifarad capacitor at this same frequency, 2 Hertz, and now you can see that the amplitude of the signal is about 104 millivolts, and the phase angle is around minus 79 degrees. So these numbers will of course give a much more realistic value for the ESR and capacitance value, and I will report those after I do the calculations. So here are the results for the 6800 microfarad cap at 2 Hertz on the lock-in amplifier. I got a measured value of 5800 microfarad. The voltage phase angle was minus 79 degrees with the loss angle being 11 degrees. ESR was very high compared to at 100 Hertz, came out to be 2.58 ohms instead of the 50 milliohms or so I was expecting. Q of 5.2 and capacitive reactance of 13.3 ohms. Not exactly sure why this measurement is way off. Perhaps somebody can comment and maybe have some measurement errors at these low frequencies. It's probably not a very practical frequency to anywhere measure it, but still be nice to know why the measurements are not quite right at this frequency. So this concludes this rather long experiment into measuring ESRs of capacitors using lock-in amplifier. Hope it was enjoyable. See you next time.